Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be introducing the concept of hydrogen bonding, a type of intermolecular attraction that exists between a specific type of molecules, but that is very, very strong, and explains the behavior of lots of molecules like water as being a classic example. So just to remind you that we've been talking recently about dipole-dipole forces, a type of intermolecular attraction that exists between things that have a permanent dipole, that is, that contains polar bonds that have a slight positive and a slight negative end. That when you have polar bonds and overall asymmetry in a molecule, that it makes that molecule polar. Okay, and we looked at water versus carbon dioxide as an example in the previous video. Okay, and so now we're going to have another look at water. Okay, so this is the structure of our water molecule. We said that each of these hydrogens had a slight positive charge and that this oxygen has a slight negative charge because that we have this overall pattern of asymmetry that can be drawn with that blue line here. But now what we see is that the oxygen, there are certain covalent bonds which are highly polar. Now these three are kind of the strongest. Okay, so we've got a bond between fluorine and hydrogen, oxygen and hydrogen, and nitrogen and hydrogen. Okay, so that is that these have the biggest difference between their positive and negative ends. That's what makes them highly polar. So the bigger the difference is between those ends, the more, the stronger that dipole is, and that therefore, then the way that those molecules interact with each other, there's a stronger attractive force here. And so we notice that these three pairings are much stronger, or kind of, they are the top echelon of polar covalent bonds, particularly the fluorine and hydrogen one, because fluorine has a much greater tendency to hang on to electrons than hydrogen does. Oxygen is kind of the next highest, and then nitrogen the next highest. You notice that they are right next to each other in the top right hand corner of the periodic table. Okay, so whereas if we say then kept that trend going and we kept looking left, that we get the carbon-hydrogen bond, and that is not polar. Okay, or it's not, the difference between those atoms is not enough to consider it to be a polar covalent bond. And so what happens is that when we get molecules that contain oxygen, and that we contain these bonds, that then they are highly polar molecules, and we get a certain type of intermolecular attraction called hydrogen bonding, okay, that exists between the polar bonds that are of this type in one molecule and another. Let me show you. Okay, so here we have two water molecules that happen to be nearby one another. And let's even kind of extend this out to add a third. Now, this is still very simple compared with your average kind of container of water molecules, but so what we see is that we have these permanent dipoles that exist, so positive and hydrogens, negative oxygens of each of these three water molecules. Now, as these come close to one another, what we see is that we get a strong attractive force that exists between the positive hydrogen and the negative oxygen in this particular case. Okay, so that we get a strong attractive force. In fact, of all the intermolecular attractions that we've looked at so far, that this is by far the strongest. Okay, because this is much more positive and this is much more negative than any other examples that we've looked at before. That this type of attractive force is what we're talking about as hydrogen bonding. Now, it doesn't just exist here. It exists here. Okay, and then it also can exist from here to another one, from here to another one, that we're getting lots of different interactions that are occurring. We can also get interactions that might occur between this one. It's not an exclusive kind of relationship. It's just all about opposite charges being brought nearer each other, and then that causing a really strong attraction. Okay, so then we get this idea called hydrogen bonding. Now, hydrogen bonding is really, really strong. It is 1/10 of strength of a covalent bond, which is very strong. Like, a covalent bond is very strong. So 1/10 of that is a significant value in terms of how much energy is involved in overcoming those attractions. Okay, and so what that then impacts is that, then we're getting significantly increased melting points and boiling points as a result of this hydrogen bonding. Okay, now what it also helps us to understand, aside from this, is that when we take a substance and we try to put it in water, then it also helps us to explain what we call solubility. That is the tendency of substances to dissolve in water or not. Okay, because let's now say I have my water molecule here. I'll put that little dipole back. Let's say that I'm trying to mix it with ethanol, which looks like this. Okay, now I haven't drawn out all the connections over here because actually it's this section is not the important bit that we need in the interaction that's over here. In fact, so ethanol also contains a polar OH bond. Okay, now this bit over here is non-polar, which has relevance to what ethanol is otherwise useful for, but it's this bit over here that we're particularly interested in right now. Actually, I'll just redraw it ever so slightly like this, just so you can see how this works. So what happens then is that you can, rather than just focusing on how water molecules attract together, that we get hydrogen bonding here too. And what that means is that then ethanol is soluble in water, okay, which is the basis of all alcoholic beverages and in fermentation and all those other sorts of things, as well as using it in solvents to dissolve things industrially. And so what we see is that a substance like ethanol is able to dissolve in water because it can be surrounded by water molecules because of these interactions that are happening. Okay, so anything that's able to undergo hydrogen bonding with water is able and is polar overall, is able to be dissolved in water effectively. Now, the reason that I make that last little comment is that let's say that this wasn't ethanol. Let's say that this is hexanol, 1-hexanol. This compound is called. So where you've actually got 6 carbons and then an OH group that's over here. Now what we can see is that this molecule does indeed, or can indeed, do hydrogen bonding with water. There is an interaction that's here. But this is where the size of this bit over here becomes relevant. This bit is non-polar. And what we can see is that it's a little bit like a seesaw. Okay, if you've got polar bits on one bit and non-polar on the other side, that the more that you stack up to bits that are non-polar versus bits that are polar, the greater the impact this has on the behavior of this molecule as a whole thing. That is, if it tends to be much more non-polar, then it's not going to be surrounded by water molecules very well. Okay, we have a principle that we'll talk about a little bit more called like dissolves like. It's worth starting, noting it down at this point so that we can unpack it a bit later. But this idea that non-polar things tend to mix with non-polar things and polar things tend to mix with polar things, but not mixing between the two. Okay, so that when most of this molecule is non-polar and there's only this tiny little polar bit down the end, this doesn't have much impact on the properties of this substance. Okay, and so that yes, it can do hydrogen bonding with water, but no, it doesn't. It won't dissolve in water very effectively because on the balance of the way this molecule behaves, it's mostly non-polar. And so what we can see is that yes, these attractions exist. Yes, they mean that substances that can do it have a much higher melting and boiling point, and we can also get, because of those interactions, we also get greater solubility, but you need to consider the molecule as a whole in terms of overall, is that molecule polar or non-polar? All right, thanks very much for watching. Bye for now.